Before we imagine a universe without stars, we must first understand just how long starlight survives. The night sky can feel eternal. For thousands of years, humans have looked upward and seen familiar patterns. The stars seem fixed, unchanging, permanent. Yet every star in the sky is living on borrowed time, and even the longest-lived stars are slowly consuming the fuel that allows them to shine. At this moment, across the observable universe, hundreds of billions of galaxies continue to glow. Their stars illuminate vast regions of space, and their light travels across millions and billions of years before reaching distant observers. The cosmos is still bright. But brightness can be deceptive. The universe today is already much quieter than it once was. Billions of years ago, galaxies produced new stars at extraordinary rates. Vast clouds of hydrogen collapsed under gravity. Stellar nurseries filled the cosmos. Young blue stars appeared everywhere. The universe was experiencing a golden age of creation. Galaxies were rich with fuel. New suns were constantly being born. New planetary systems emerged from swirling disks of gas and dust. The cosmos was busy building itself. But every star requires something precious. Hydrogen. Hydrogen is the simplest element in existence. It formed shortly after the universe itself began. For billions of years, stars have steadily converted that hydrogen into heavier elements. Each generation leaves a little less fuel behind for the next. Slowly, almost imperceptibly, the universe has been spending a finite supply of fuel. And unlike a civilization, it has no way to create more. Imagine a city powered entirely by stored energy. For a long time, the lights shine brightly. Factories operate. Streets remain illuminated. Life continues as normal. Then, gradually, the reserves begin to shrink. Nothing changes overnight. The city remains active. But fewer new lights are installed. More old lights burn out. The balance slowly shifts. The universe faces a similar future. For trillions of years to come, stars will continue shining. Many of the stars visible today will die. Others will take their place. The cosmos will still appear alive. Yet beneath the surface, an irreversible trend is unfolding. The total supply of star-forming material is decreasing. Every supernova, every stellar wind, every generation of stars pushes the universe one step closer to a future where creation becomes increasingly difficult. Fortunately, the process is extraordinarily slow. Human civilizations rise and fall in thousands of years. Species evolve over millions. Planets change over billions. The universe thinks in trillions. The stars that will survive the longest are not giant stars like the Sun. They are much smaller, much dimmer. Red dwarfs. These humble stars possess a remarkable advantage. They burn their fuel with extraordinary efficiency. Some may continue shining for trillions of years. Long after stars like the Sun have vanished, the red dwarfs will remain. In the unimaginably distant future, they will become the final sources of natural starlight. The last beacons in an increasingly dark universe. If any observers still exist during those distant ages, they would witness a very different cosmos. Most galaxies would already be aging. Most bright stars would be gone. The heavens would grow quieter with every passing trillion years. Yet scattered throughout the darkness, a few stubborn stars would continue to shine. Tiny, ancient, patient. They would outlive almost everything. But even red dwarfs cannot burn forever. Their fuel is finite. Their light will eventually fade. And after spans of time so vast that they defy human comprehension, the final generation of stars will approach the end of their lives. The universe will experience something it has never experienced before. Not the death of a single star. Not the death of a galaxy. But the end of starbirth itself. For the first time since the cosmos was young, no new stars will emerge from the darkness. And when that moment arrives, the universe enters an entirely new age. An age where the lights slowly begin to go out. The end of starbirth does not mean the universe suddenly becomes dark. There is no final sunset. No moment when galaxies abruptly vanish into blackness. The event passes almost unnoticed. Across the cosmos, countless stars continue shining exactly as they did before. Galaxies still glow. Ancient suns continue producing light. If an observer could somehow witness the moment when the last new star was born, they might not realize anything had changed at all. And yet everything has changed. For the first time since the universe was young, the cosmos is no longer creating new sources of light. Every star that will ever exist has already been born. The great stellar factories that once transformed clouds of gas into brilliant suns have fallen silent. What remains is a universe living on its savings. Imagine a civilization that has stopped earning new income. The cities remain active. The lights remain on. Life appears normal. Yet every day, a little more money leaves the account than enters it. The change is invisible at first. Years may pass before anyone notices. But eventually the consequences become unavoidable. The universe now faces a similar reality. The stars that illuminate the galaxies are no longer part of a renewable cycle. Each one represents a limited reserve of energy. Some will shine for millions of years. Others for billions. The smallest stars may survive for trillions. But none are permanent. Every star that disappears reduces the total amount of light in the cosmos, and no future generation will arrive to replace it. Time continues to move forward. Millions of years pass. Then billions. Then trillions. Throughout this immense span of time, the universe slowly changes character. Bright young stars become increasingly rare because there are no young stars left. Stellar populations grow older together. Galaxies that once contained stars of every age gradually become dominated by ancient survivors. The night skies of the distant future would look very different from the ones we know today. Many of the brilliant stars familiar to modern astronomers would already be gone. Massive stars would have disappeared long ago. Sun-like stars would have completed their life cycles and faded into stellar remnants. The heavens would still contain light, but much of the variety that once defined the universe would be gone. The cosmos would begin to feel older, quieter, more patient. Entire galaxies would spend trillions of years changing very little. The violent events that once shaped cosmic history would become increasingly uncommon. Fewer supernovae would erupt across the darkness. Fewer stars would undergo dramatic transformations. The universe would settle into a slower rhythm, one measured not in explosions and creation, but in gradual decline. And yet pockets of light would remain. Scattered throughout the galaxies, countless red dwarfs would continue their long existence. These small stars would become the dominant sources of starlight in the universe. To any distant observer, they would appear as the final embers of a fire that once illuminated the cosmos. Many of them would shine for periods so long that they challenged the imagination. Entire mountain ranges could rise and erode away on Earth trillions of times over before some of these stars exhausted their fuel. They would witness ages of cosmic history far beyond anything experienced by larger stars. But even the most patient stars cannot escape time forever. One by one, the remaining lights would begin to disappear. Not quickly. not dramatically, but steadily. A red dwarf here. Another there. Then another. Across unimaginable spans of time, the population of shining stars would continue to shrink. The process would be so slow that no observer could ever watch it unfold directly. Yet the outcome would already be written into the laws of physics. The universe had stopped creating stars. Now it was waiting for the last ones to die. And among those final survivors, a remarkable group of stars would endure longer than almost anything else in existence. They would become the last natural sources of light the universe would ever know. The story of the end now belongs to them. For most of cosmic history, red dwarfs were easy to overlook. They are the smallest true stars in the universe. Dimmer than the sun. Cooler than the stars that dominate familiar night skies. If one of them replaced our sun, daylight on Earth would become dramatically weaker. The sky would appear different. The warmth that sustains life would diminish. By the standards of human experience, red dwarfs seem unremarkable. Yet appearances can be misleading. Throughout the long history of the cosmos, the brightest stars have received most of the attention. Massive blue stars illuminated galaxies with extraordinary brilliance. Some shined hundreds of thousands of times brighter than the sun. They lived dramatic lives and often ended in spectacular explosions. Even stars like our sun seemed far more important than the faint red dwarfs, scattered throughout the Milky Way. But the future does not belong to the brightest stars. It belongs to the longest-lived ones. A massive star may survive for only a few million years before exhausting its fuel. The sun will endure for roughly 10 billion years. Red dwarfs operate on an entirely different scale. They consume their hydrogen so slowly and so efficiently that some are expected to survive for trillions of years. They are not the sprinters of the universe. They are the marathon runners. As the ages pass and larger stars disappear, the red dwarfs remain. One by one, the giants vanish. Blue stars disappear first. Then stars similar to the sun. Entire generations of stellar objects come and go while the red dwarfs continue shining almost unchanged. Trillions of years flow by, and these small stars simply continue their patient existence. The universe around them grows older. Galaxies become quieter. Stellar remnants accumulate. Ancient white dwarfs drift through the darkness. The violent events that once shaped cosmic history become increasingly rare. Yet throughout this immense span of time, red dwarfs continue producing light. They become the dominant stars of the cosmos, not because they are powerful, but because they refuse to die. If an observer existed during this distant era, the night sky would be profoundly different from our own. The brilliant variety of stars familiar to modern astronomy would be largely gone. Most of the remaining light would come from countless red dwarfs, scattered across aging galaxies. The heavens would appear dimmer, older, more subdued. Yet light would still exist. The universe would still possess a heartbeat. By now, unimaginable stretches of time have already passed. Entire chapters of cosmic history have come and gone. Civilizations, if any ever existed elsewhere in the universe, would be separated from these distant ages by intervals so vast that they would appear almost meaningless. The stars visible today would be ancient history. Even galaxies themselves would look different. Yet the red dwarfs endure. They continue converting hydrogen into helium. Slowly. Patiently. Efficiently. Their remarkable longevity comes from the way they use their fuel. Unlike stars such as the sun, which consume only a portion of their available hydrogen, red dwarfs can mix much of their material throughout their interiors. This allows them to use a far greater fraction of their fuel supply. They waste very little. In a universe increasingly defined by scarcity, efficiency becomes survival. But survival is not immortality. Even the most efficient machine eventually runs out of fuel. Even the longest story eventually reaches its final chapter. Trillions of years become tens of trillions. Tens of trillions become hundreds of trillions. The oldest red dwarfs begin approaching the limits of their extraordinary lifespans. For the first time, the universe starts losing the very stars that once seemed eternal. The process unfolds, slowly beyond imagination. One star fades, then another. Vast stretches of time separate each event. The darkness grows not through catastrophe, but through accumulation. Every disappearing red dwarf removes another source of light from the cosmos. Every fading star leaves the universe slightly dimmer than before. Eventually, an extraordinary period arrives. The cosmos contains only a small population of surviving stars. Across entire galaxies, light becomes increasingly rare. Immense regions of space that once contained billions of shining suns now contain only scattered remnants of a brighter past. The remaining red dwarfs become precious. They are no longer ordinary stars. They are the final stars. The last guardians of starlight. The last natural furnaces still producing energy through fusion. The last objects keeping complete darkness at bay. And then their numbers continue to fall. One by one. Patiently. Inevitably. Until a moment approaches unlike any other in cosmic history. A moment that no universe had ever experienced before. Somewhere in the vast darkness, a single star continues to shine. One final red dwarf. One final point of natural starlight surrounded by an ocean of blackness. Its light may travel for millions of years without encountering another star. Entire galaxies may already have fallen silent. Yet for a little while longer, the universe is not completely dark. One star remains. But not for much longer. The story of starlight, which began billions of years after the birth of the universe, is finally approaching its conclusion. And when the last red dwarf exhausts the final reserves of fuel within its core, the cosmos will witness its final sunset. For the first time since stars began to exist, there will be no starlight anywhere in the universe. The age of stars will be over. For trillions upon trillions of years, the universe continued to produce light. The galaxies had long since stopped creating new stars, and the great stellar nurseries that once filled the cosmos had become silent relics of a distant past. Yet scattered throughout the darkness, a small population of red dwarfs continued shining. They endured through ages so vast that entire chapters of cosmic history seemed brief by comparison. One by one, their numbers declined. One by one, the lights disappeared. Until eventually only a handful remained. Then only a few. Then only one. Somewhere within the immense darkness of the universe, a final star continued to shine. It was not a giant blue star visible across galaxies. It was not a star like our Sun. The last survivor was almost certainly a red dwarf. Small. Dim. Efficient. A star that had spent trillions of years carefully conserving its fuel while brighter and more powerful stars exhausted theirs long ago. It had outlived stars, planets, galaxies as we know them, and perhaps every civilization that had ever existed beneath the light of the cosmos. By this point, the universe would be almost unrecognizable. The stars familiar to us today would have vanished ages earlier. Most stellar remnants would have spent unimaginable spans of time drifting through ancient galaxies. Entire regions of the cosmos would already be dark. Yet one small star continued producing light. One final furnace still converting matter into energy. One final reminder of an era when the heavens were filled with countless suns. If an observer existed nearby, the scene would seem strangely ordinary. The last star would not announce its importance. It would rise and shine as it always had. Light would continue streaming outward into space. Fusion, reactions would continue deep within its core. Nothing dramatic would suggest that this object carried the final chapter of stellar history within it. To any observer watching only a few years or even a few million years, it would appear unchanged. But the countdown would be approaching its end. For trillions of years, gravity and fusion had remained in balance inside the star. Gravity pulled inward while energy pushed outward. This delicate struggle sustained the star's existence and allowed it to shine across unimaginable stretches of time. Yet every second consumed a tiny amount of the remaining fuel. Every second moved the star slightly closer to a future that could no longer be avoided. The process was slow beyond comprehension, but it was relentless. Eventually, the fuel supply would become insufficient. The reactions inside the core would begin to weaken. Energy production would decline. The balance that had maintained the star for so long would slowly start to fail. There would be no spectacular explosion visible across the universe. No final burst of light announcing the end of an age. The last star would simply begin losing the ability to remain a star. Its light would fade. Slowly. Patiently. Inevitably. Over immense spans of time, the energy leaving its surface would decrease. The warmth it produced would diminish. The final source of natural starlight in the universe would be approaching extinction. The darkness surrounding it would not advance dramatically. Instead, the light itself would quietly retreat. And then, at some moment impossible to predict, fusion would finally cease. The great process that powered the stars for nearly the entire history of the cosmos would come to an end. No hydrogen would remain available for fusion. No new energy would be generated within the core. The engine that illuminated galaxies, forged heavy elements, and made planets and life possible would finally stop. What began billions of years after the birth of the universe would now reach its conclusion. The universe would experience something entirely new. For the first time since the earliest stars ignited, there would be no active stars anywhere in existence. No stellar nurseries. No young suns. No aging red giants. No red dwarfs quietly burning in distant galaxies. The age of starlight would be over. Every beam of light still traveling through space would be a messenger from the past, emitted long before the final star disappeared. The significance of that moment is difficult to overstate. Stars shaped nearly everything familiar in cosmic history. They illuminated galaxies, created the elements needed for planets, powered ecosystems, marked the passage of time across the universe. Every civilization that ever looked into the heavens did so beneath the light of stars. Every living creature that ever existed ultimately depended on energy produced inside a stellar core. For almost the entire history of the cosmos, stars were the defining feature of reality itself. Now that chapter would be finished. Yet the universe would not become completely empty. The final star would leave something behind. Its fusion would end, but its matter would remain. The object would continue existing as a stellar remnant, carrying the memory of a once luminous past. Across the cosmos, countless other remnants already filled the darkness. White dwarfs. Neutron stars. Black holes. The remains of stars that had died across unimaginable spans of time. The universe was no longer a place of living stars. It had become a universe of remnants. A vast cosmic graveyard now stretched across the darkness. The lights had gone out. The fires had cooled. What remained were the silent remains of a brighter age. But even in death, stars were not finished shaping the future. Their remnants would dominate the next great chapter of cosmic history. And among those remnants, one type of object would vastly outnumber all the others: the white dwarfs. The death of the last star did not leave the universe empty. Light produced by fusion had disappeared, but the cosmos remained filled with the remnants of a much brighter age. Across ancient galaxies, countless stellar corpses continued drifting through the darkness. White dwarfs, neutron stars, black holes. The remains of stars that had lived and died over spans of time almost impossible to comprehend. The universe had entered a new chapter, one no longer defined by living stars, but by the objects they left behind. Among these remnants, one type dominated the cosmos: white dwarfs. For billions of years, stars similar to the Sun ended their lives in the same way. After exhausting their fuel, they shed their outer layers and exposed their dense cores. What remained was a white dwarf. An object roughly the size of Earth containing a significant fraction of a star's original mass. During the age of starlight, white dwarfs were common. During the age of remnants, they became almost everywhere. If an observer could travel across the universe during this era, they would find galaxies transformed beyond recognition. The bright spiral arms that once defined galaxies like the Milky Way would have faded long ago. The brilliant blue stars that illuminated cosmic history would be gone. In their place would be enormous populations of white dwarfs, slowly orbiting through ancient gravitational structures. The universe would still contain matter. It would still contain motion. But much of the familiar light would have vanished. At first, many white dwarfs would continue glowing. They would radiate heat left over from their former lives as stars. Some would shine with a faint white light. Others would appear reddish as they cooled. Yet unlike true stars, they were no longer generating energy through fusion. They were living on stored heat, slowly releasing energy accumulated during billions of years of stellar evolution. Imagine removing the fire from a furnace while leaving the metal glowing hot. For a long time, warmth would remain. The furnace would continue radiating heat into its surroundings. But no new energy would be created. The glow would gradually weaken. Eventually, the warmth would disappear entirely. White dwarfs faced a similar future. Time continued its relentless march forward. Trillions of years passed. Then quadrillions. The white dwarfs slowly surrendered their heat to space. Their temperatures dropped. Their light diminished. What once had been the brilliant cores of living stars became increasingly faint. The process was extraordinarily slow, far slower than the lifetimes of civilizations, planets, or even stars themselves. Yet given enough time, the outcome was unavoidable. The universe had lost its stars. Now it was beginning to lose the remnants of those stars as well. Throughout this immense era, encounters between objects became increasingly rare. The universe itself continued expanding. Distances between large structures grew larger. Ancient galaxies remained gravitationally bound, but much of the cosmos beyond them disappeared from view. Observers living during this age would see a universe far smaller than the one we observe today. Most galaxies would have slipped permanently beyond the cosmic horizon, carried away by the expansion of space. The surviving islands of matter would grow increasingly isolated. Within these islands, white dwarfs would continue their silent existence. Occasionally, gravity would bring two remnants close together. Rare collisions might occur. Binary systems would slowly evolve. Some white dwarfs could merge, producing brief flashes of activity in an otherwise quiet universe. But such events would become exceedingly uncommon. The dominant characteristic of this era was not violence. It was patience. The cosmos had become a place of waiting. Every white dwarf carried the same destiny. No matter how hot it once was. No matter how massive its parent star had been. No matter how brightly it shined during its youth. Eventually, it would cool. The stored heat would radiate away. The faint glow would disappear. The remnant would become darker and darker as unimaginable spans of time passed. By now, the universe would feel profoundly different from anything familiar to us. There would be no bright constellations. No glowing nebulae. No stellar nurseries filled with newborn suns. The sky, if such a concept still existed, would be dominated by darkness. Scattered points of faint light would remain, but even those were slowly fading. The cosmos seemed to be moving toward a future where light itself would become increasingly rare. Yet the white dwarfs endured. For spans of time so vast that the entire age of stars seemed brief by comparison, they continued cooling. They became the most common visible objects in the universe. Ancient monuments to a time when fusion illuminated galaxies. Silent witnesses to the long decline of cosmic light. But even their story would not last forever. As trillions became quadrillions and quadrillions became numbers almost beyond description, the last traces of heat would finally disappear. The white glow that gave these remnants their name would fade completely. Their surfaces would cool until they became nearly indistinguishable from the darkness surrounding them. The universe was approaching another threshold. The age of white dwarfs was ending. And a new era was about to begin. An era populated by objects that had never been observed by any civilization. Objects predicted by physics, but so ancient that the universe itself had not yet lived long enough to create one. Black dwarfs. For an unimaginably long time, white dwarfs remained the dominant objects in the universe. They drifted through ancient galaxies as fading reminders of a brighter age. Long after the last star had died, these stellar remnants continued radiating the heat they had carried from their former lives. Their glow was faint. Their energy reserves were limited. Yet for spans of time so vast that the entire age of starlight seemed brief by comparison, they remained visible. But nothing in the universe escapes the passage of time. White dwarfs do not produce new energy. Unlike living stars, they possess no internal furnace replenishing the heat that escapes into space. Every second, a tiny amount of energy leaves their surfaces and travels outward into the darkness. The loss is almost imperceptible. Even after trillions of years, many white dwarfs would still retain some warmth. Yet the process never stops. Time continues forward. Heat continues outward. The temperature continues to fall. Imagine removing a glowing ember from a fire. At first it shines brightly. Hours later it still radiates warmth. Given enough time, the glow disappears. The ember becomes dark and cold, almost indistinguishable from its surroundings. White dwarfs face the same destiny, although their transformation unfolds over timescales so immense that ordinary language struggles to describe them. As quadrillions of years pass, the universe enters a period unlike anything that came before. The last traces of stellar warmth gradually vanish. White dwarfs that once glowed faintly across the darkness become increasingly difficult to see. Their surfaces cool. Their light fades. Their temperatures slowly approach the temperature of the surrounding universe. The difference between the remnant and the darkness around it becomes smaller and smaller. Eventually, the transition is complete. The white dwarf is no longer white. It is no longer glowing. It no longer radiates enough visible light to be seen across space. What remains is an object astronomers call black dwarf. Despite the name, black dwarfs are not black holes. They are the final evolutionary stage of stars like our Sun. Dense, cold, dark. The ancient cause of stars that exhausted their fuel so long ago that even their residual heat has finally disappeared. In our present universe, black dwarfs do not yet exist. The cosmos is simply not old enough. The first white dwarfs have not had sufficient time to cool into this final state. But in the distant future, they will be everywhere. Entire galaxies will become populated by these dark stellar remnants. Objects that once illuminated planetary systems and contributed to the evolution of galaxies will now drift silently through space. They will contain the same mass, the same structure, the same history. Yet their light will be gone. To an outside observer, they would be nearly invisible against the darkness of the universe. The transformation carries a deeper meaning than the cooling of individual stars. For most of cosmic history, light served as the defining characteristic of the universe. Stars illuminated galaxies. Supernovae exploded across space. Nebulae glowed with vibrant colors. Even white dwarfs preserved a faint reminder of that luminous past. Now the situation is changing. The universe is no longer merely losing stars. It is losing visible light itself. Darkness becomes the dominant condition of existence. If an observer somehow survived into this era, the heavens would appear profoundly different from anything familiar to us. There would be no bright stars decorating the sky. No glowing bands of starlight stretching across galaxies. No brilliant clusters illuminating the darkness. Instead, most of the matter in the universe would exist as invisible remnants drifting through immense expanses of empty space. The universe would still contain extraordinary numbers of objects. But seeing them would become increasingly difficult. Gravity would remain. Matter would remain. Motion would remain. Yet light, the phenomenon through which civilizations once understood the cosmos, would be disappearing. The universe would begin resembling a vast collection of unseen objects moving through an ocean of darkness. And still, time continues. The black dwarfs themselves appear permanent. They are stable, cold, inactive. For immense spans of time, they simply exist. Trillions become quadrillions. Quadrillions become quintillions. The dark remnants continue orbiting through ancient gravitational systems that have survived from earlier eras. At first glance, it may seem as though cosmic evolution has finally come to an end. But the universe is not finished changing. Even in darkness, gravity continues its work. Occasionally, black dwarfs pass near one another. Ancient stellar remnants drift through crowded regions left behind by long-dead galaxies. Over enough time, rare encounters become inevitable. Some objects are ejected into intergalactic space. Others collide. Some fall toward black holes. The universe may appear frozen, but subtle changes continue unfolding across timescales that dwarf everything that came before. The age of black dwarfs is quiet, patient, almost motionless. Yet beneath that stillness, gravity is slowly reshaping the future. The stars are gone. Their remnants have gone dark. The cosmos has become a place of cold matter drifting through endless darkness. But scattered throughout that darkness are objects far stranger than black dwarfs. Objects that survived every previous chapter of cosmic history. Objects whose influence extends across billions of light years and unimaginable spans of time. Black holes. And in the ages to come, they will become the dominant rulers of the universe. As the age of black dwarfs unfolds, the universe appears quieter than ever before. The stars are gone. Their remnants have cooled into darkness. Ancient galaxies drift through space as vast collections of invisible objects orbiting one another across immense distances. To a casual observer, it might seem as though cosmic history has finally reached its conclusion. The great dramas of creation and destruction that once shaped the universe appear to be over. But hidden within the darkness are objects that have been waiting for this moment. Black holes. They first appeared during the age of stars. Some formed when massive stars exhausted their fuel and collapsed under their own gravity. Others grew over billions of years at the centers of galaxies, consuming gas, dust, stars, and even other black holes. During earlier eras, they were important participants in cosmic history. In the distant future, they become something far greater. They become the dominant structures of the universe. A black hole is unlike any other object in nature. It possesses gravity so intense that once something crosses a boundary known as the event horizon, escape becomes impossible. Not matter. Not planets. Not stars. Not even light itself. Everything that passes beyond that boundary is permanently removed from the visible universe. During the age of starlight, black holes often hid within bright galaxies filled with billions of stars. Their presence was revealed indirectly through the motion of nearby matter or by the intense radiation generated as material spiraled inward. But the future universe is different. The stars are gone. The galaxies are dark. Many of the objects that once competed for attention have disappeared. The black holes remain. For unimaginable spans of time, gravity slowly reshapes the contents of ancient galaxies. Orbits that once seemed stable begin to change through countless gravitational interactions. Black dwarfs pass near one another. Neutron stars exchange momentum. Objects are occasionally thrown into intergalactic space. Others slowly migrate inward toward the gravitational centers of their galaxies. The process is extraordinarily slow, but the universe has time to spare. Over enough time, many of these ancient remnants meet the same fate. They fall into black holes. A black dwarf that spent quadrillions of years drifting through darkness may eventually wander too close. A neutron star may lose orbital energy and spiral inward. Even smaller black holes can be captured by larger ones. One by one, the contents of galaxies are gradually consumed. The process unfolds so slowly that no single event appears significant. Yet over spans of time that dwarf all previous eras, the cumulative effect becomes profound. The black holes grow. Not rapidly. Not dramatically. But steadily. Imagine watching a forest disappear one leaf at a time. Any individual change would seem insignificant. Yet eventually the forest would be gone. The future of galaxies unfolds in a similar manner. Every object swallowed by a black hole slightly increases its mass. Every merger creates a larger gravitational giant. Over immense stretches of time, black holes inherit the matter that once belonged to stars, planets, and stellar remnants. The largest among them become truly extraordinary. At the centers of ancient galaxies reside supermassive black holes containing millions or even billions of times the mass of the Sun. These objects already exist in the present-day universe. In the distant future, many will become even larger as they absorb the remnants surrounding them. Some may eventually merge with one another, creating gravitational monsters unlike anything found during the age of stars. By now, the appearance of the universe would be almost impossible for modern humans to recognize. Most visible objects have disappeared. Most matter exists either as cold remnants or inside black holes. The brilliant structures that once filled astronomical photographs are gone. No glowing nebulae. No spiral galaxies illuminated by starlight. No clusters of young suns. The universe has become darker, simpler, and far quieter. Yet black holes continue to shape everything around them. Their influence extends far beyond their event horizons. Gravity continues organizing matter across enormous distances. Even when invisible, black holes determine the motions of surrounding objects. They become the anchors around which the remaining structures of the universe evolve. In many ways, the future cosmos belongs to them. For an unimaginably long period, black holes appear almost eternal. Stars live for millions, billions, or trillions of years. White dwarfs cooled over quadrillions of years. Black holes endure for timescales that make all previous eras seem brief. If an observer somehow witnessed the future unfold across these vast ages, black holes would appear to be the only truly permanent inhabitants of the cosmos. But appearances can be deceptive. Earlier generations looked at stars and imagined they would shine forever. Later generations might look at black holes and reach the same conclusion. Yet the universe has repeatedly demonstrated that permanence is often an illusion. Even the most stable objects eventually encounter limits imposed by the laws of physics. The black holes seem invincible. They consume matter. They survive while stars vanish. They persist while galaxies fade. They dominate an increasingly dark universe. Yet hidden within the mathematics of nature lies a remarkable discovery. A discovery that suggests black holes are not truly eternal. They are dying. The process is so slow that it remained completely unknown until the 20th century. It produces no dramatic explosion at first. No visible warning. Yet every black hole in existence is gradually losing energy. Every black hole carries within it an invisible countdown. And while that countdown may last for durations beyond imagination, it is moving forward nonetheless. The age of black holes is only a chapter. And eventually, even these cosmic giants will begin to disappear. For most of cosmic history, black holes appeared to be the ultimate survivors. Stars were born and died. Galaxies evolved. White dwarfs cooled into darkness. Entire eras of cosmic history came and went. Yet the black holes remained. They consumed matter. They grew larger. They inherited the contents of ancient galaxies. To any observer living during the age of black holes, these objects would seem eternal. Nothing could escape them. Nothing could destroy them. They appeared to be the final destination of matter itself. But the universe has a habit of challenging assumptions. In 1974, physicist Stephen Hawking made a remarkable discovery. By combining ideas from quantum mechanics and gravity, he found that black holes are not completely black. They do not simply absorb energy forever. Instead, they slowly release tiny amounts of energy back into the universe. The process is now known as Hawking radiation. The effect is extraordinarily small. For the black holes that exist today, the amount of energy emitted is so tiny that it is essentially impossible to detect. A black hole absorbs far more energy from its surroundings than it loses through Hawking radiation. During the present age of the universe, the process has almost no practical consequences. Black holes continue growing while the radiation remains insignificant. But the future universe is very different. The stars are gone. The galaxies have faded. Most matter has already been consumed or scattered across immense distances. The black holes are increasingly isolated. With little new material available to absorb, Hawking radiation begins to matter. The process remains incredibly slow, but for the first time, black holes start losing more energy than they gain. The evaporation has begun. Imagine an enormous block of ice floating in a desert. At first the change is impossible to notice. A few molecules leave the surface. Then a few more. Days pass. Years pass. The block still appears unchanged. Yet the loss continues. Given enough time, even the largest block eventually disappears. Hawking radiation operates in a similar way. Every moment, a tiny amount of energy escapes. Every moment, the black hole becomes slightly less massive than before. The timescales involved are almost beyond comprehension. A black hole containing the mass of the Sun would require approximately 10 to the power of 67 years to evaporate completely. Supermassive black holes, the giants residing at the centers of ancient galaxies, would survive far longer. Some may persist for 10 to the power of 100 years or more. These numbers are so large that the entire age of the universe today becomes almost insignificant by comparison. Everything humanity has ever known occupies only an invisible fraction of these durations. For an unimaginably long period, black holes continue dominating the cosmos. Ancient galaxies become collections of black holes and scattered remnants drifting through darkness. The universe remains quiet, cold, empty. Yet beneath this stillness, the evaporation continues. The largest structures in existence are slowly surrendering their mass to space. At first, the changes are impossible to notice. Then, over immense spans of time, they become measurable. The black holes shrink. Very gradually, their event horizons contract. Their masses decrease. The process accelerates as they become smaller. A large black hole evaporates slowly. A smaller black hole evaporates more quickly. As the mass declines, the rate of energy loss increases. The countdown that once seemed frozen begins moving faster. The future universe would witness a strange reversal of cosmic history. Earlier eras were defined by growth. Stars formed from gas clouds. Galaxies merged into larger galaxies. Black holes consumed matter and increased in size. Now the trend moves in the opposite direction. The largest objects in the universe are becoming smaller. The giants that once dominated entire galaxies are steadily disappearing. One by one, ancient black holes reach their final moments. After durations so vast they defy imagination, a black hole that has spent nearly its entire existence evaporating approaches the end of its life. The process that began almost imperceptibly now accelerates dramatically. The remaining mass is released in a final burst of energy. For a brief moment, one of the darkest objects in the universe becomes one of the brightest. Then it is gone. The event would be extraordinary. A flash emerging from a universe that has spent countless ages growing darker. Yet there would be no audience to witness it. No stars illuminating nearby space. No planets orbiting in the darkness. No galaxies bustling with activity. The explosion would occur within a universe that has already outlived nearly every familiar structure. And still the process continues. Across unimaginable spans of time, more black holes disappear. Smaller ones vanish first. Larger ones follow later. The greatest supermassive black holes endure the longest, resisting evaporation for durations that make all previous eras seem brief. Yet even they cannot escape forever. Hawking radiation is patient. It never stops. It never weakens. Given enough time, it always wins. Eventually, a remarkable moment arrives. The final black hole approaches the end of its existence. For countless ages, black holes dominated the universe. They survived the death of the stars. They survived the cooling of white dwarfs. They survived the transformation of galaxies into dark collections of remnants. They seemed permanent when everything else disappeared. Yet now the last of them is preparing to vanish. Its final burst of radiation spreads into the darkness. The event horizon disappears. The black hole ceases to exist. For the first time since the earliest stars collapsed billions of years after the Big Bang, there are no black holes anywhere in the universe. Another chapter of cosmic history has ended. The stars are gone. The white dwarfs are gone. The black dwarfs are gone. The black holes are gone. The great structures that once shaped the universe have all disappeared. What remains is a cosmos more empty than anything that came before. A universe where even matter itself may no longer be safe from the passage of time. And that leads to an even deeper question. What happens when the universe begins to lose matter itself? After the last black hole disappears, the universe enters one of the strangest chapters in its history. For nearly everything we have discussed so far, there was always something familiar remaining. When stars died, their remnants survived. When white dwarfs cooled, black dwarfs remained. When black holes evaporated, their energy continued spreading through space. The universe was changing, but it was still made of things. Matter persisted. Structure persisted. There was always something left behind. Now even that assumption begins to unravel. Matter feels permanent to us because it forms the foundation of our experience. Every mountain, ocean, planet, star, and living creature is built from atoms. The air we breathe, the ground beneath our feet, and the galaxies scattered across the cosmos all depend on the existence of matter. It is easy to imagine stars disappearing. It is much harder to imagine matter itself vanishing. Yet modern physics suggests that permanence may be an illusion. At the center of this idea lies a question scientists have debated for decades. Are protons truly stable? A proton is one of the fundamental building blocks of ordinary matter. Every atom contains them. Every planet contains them. Every object you have ever touched contains unimaginable numbers of protons. If protons last forever, matter may survive indefinitely. But if protons eventually decay, then every structure built from ordinary matter carries an invisible countdown. No experiment has ever observed a proton decay. As far as current observations can tell, protons are extraordinarily stable. Their lifetimes, if finite, must be at least tens of billions of years. Yet some theories in physics predict that proton decay is possible. If those theories are correct, the consequences for the distant future are profound. Imagine a stone resting quietly in the darkness of the future universe. It no longer orbits a star because the stars are gone. It no longer belongs to a planet because the planets have long since been destroyed or scattered. It simply exists. Stable. Unchanging. Seemingly eternal. Yet deep within the atoms that compose the stone, protons may slowly and randomly disappear. The process would be unimaginably rare. A single proton might survive for periods that make the age of stars seem insignificant. But the universe possesses one advantage over every other system. Time. Enough time passes for even the rarest events to become inevitable. What appears impossible across billions of years may become unavoidable across intervals measured in powers of 10 so large they barely fit on a page. If proton decay occurs, matter throughout the universe gradually begins to disassemble. Not suddenly. Not dramatically. The process unfolds with extraordinary patience. Ancient remnants that survived the death of stars and black holes slowly lose the particles that hold them together. Atoms cease to exist. Molecules break apart. Structures that remain stable for unimaginable spans of time begin dissolving into simpler forms. The universe does not explode. It simply forgets how to remain assembled. The transformation affects everything. The cold remnants of ancient stars. The scattered debris left behind by galaxies. any planets that somehow survived the previous eras. Every object built from ordinary matter slowly begins surrendering its existence. Given enough time, even the most durable structures become temporary. The scale of this future is almost impossible to comprehend. Earlier chapters of cosmic history unfolded across billions or trillions of years. The era of black holes extended far beyond that. Proton decay, if it occurs, operates on timescales that dwarf all previous ages. By now, the universe has become older than anything human language was designed to describe. Entire eras that once seemed eternal have become brief episodes in a much larger story. And still, time continues forward. As matter gradually disappears, the universe becomes increasingly empty. The objects that once filled space become rarer. Ancient structures vanish. The distinction between something and nothing begins to blur. What remains is a diffuse collection of particles and radiation spread across an ever-expanding cosmos. The rich complexity that once defined the universe gives way to extraordinary simplicity. If an observer somehow existed during this era, they would inhabit a reality almost impossible to recognize. There would be no stars overhead. No galaxies decorating the heavens. No planets. No black holes. No familiar structures of any kind. Space would stretch in every direction, containing only isolated particles separated by immense distances. The universe would feel less like a place and more like an absence. Yet even here, the story may not be finished. The fate of matter depends on laws of physics that remain uncertain. Proton decay has never been observed. It remains a prediction rather than a confirmed fact. If protons truly last forever, some matter may survive indefinitely. If they do not, then the universe eventually becomes a far emptier place than anything we have yet imagined. Either way, a deeper trend remains unmistakable. The cosmos is becoming simpler. The complexity that once produced galaxies, stars, planets, oceans, ecosystems, and civilizations is gradually fading away. The universe is not moving toward greater structure. It is moving toward less. Energy becomes more evenly distributed. Matter becomes increasingly dispersed. Differences disappear. Contrasts fade. The cosmos slowly drifts toward a state where almost nothing happens. This idea is sometimes called the heat death of the universe. Not because the universe becomes hot, but because useful energy becomes unavailable. The great engines that once powered cosmic evolution have all shut down. No stars remain to illuminate the darkness. No black holes remain to shape the future. No major structures remain to create change. The universe approaches a condition of extraordinary stillness. And beyond that stillness lies the final question. What does a universe look like when almost everything that could happen has already happened? What remains when the stars are gone, the black holes are gone, and even matter itself has begun to disappear? The answer takes us to the final chapter of our journey. A chapter set so far in the future that the universe itself has become almost unrecognizable. A universe approaching its ultimate fate. We began our journey in a universe filled with light. Galaxies stretched across the cosmos. Stars illuminated the darkness. Planets orbited distant suns. Entire civilizations could look upward and wonder about their place among the heavens. The universe was active, dynamic, full of structure and possibility. Yet throughout this documentary, we have followed a single question into the farthest reaches of time. What happens after the last star dies? Now we have our answer. The stars are gone. Their remnants have cooled into darkness. Black holes have evaporated. Matter itself may be slowly disappearing. The familiar universe that once existed has faded almost completely from reality. What remains is a cosmos so different from our own that it challenges the limits of imagination. The future universe is defined by emptiness. Not the emptiness we experience between planets or stars. Not even the emptiness between galaxies. Those regions still contain matter, radiation, magnetic fields, and traces of structure. The emptiness of the far future is something deeper. Space stretches across unimaginable distances containing almost nothing at all. Particles become isolated by expanses, so vast that encounters grow increasingly rare. The universe continues expanding, and with every passing age, those separations become even greater. Time itself begins to lose its meaning. Throughout history, time was measured through change. Planets orbited stars. Stars evolved. Galaxies collided. Black holes consumed matter. Events occurred. Processes unfolded. The passage of time could be observed because the universe was constantly transforming. But in the far future, change becomes increasingly uncommon. Millions of years pass. Then billions. Then periods so large they cannot easily be described. Yet almost nothing happens. Imagine sitting in a room where every clock has stopped. The room remains. Space still exists. Yet the familiar markers that once measured the passage of time have vanished. The future universe resembles this strange condition on a cosmic scale. Reality continues existing, but the events that once defined cosmic history have largely disappeared. The universe enters a state of extraordinary stillness. If proton decay occurs, even the remaining particles continue disappearing. Matter gradually dissolves into simpler forms of energy. If proton decay does not occur, isolated particles may survive indefinitely. Either possibility leads toward a similar destination. The universe becomes increasingly dilute, increasingly uniform, increasingly empty. Differences between one region and another slowly fade away. The cosmos approaches equilibrium. This idea is often described as heat death. It does not mean the universe burns. It does not mean a final explosion occurs. Instead, it represents the gradual loss of useful energy. Earlier eras were filled with imbalance. Hot stars existed beside cold space. Matter gathered into galaxies. Gravity created structure. Energy flowed from one place to another. These differences made change possible. They powered everything from stellar evolution to life itself. Eventually, those differences disappear. Energy becomes distributed more evenly throughout the universe. Temperature differences diminish. Opportunities for meaningful change become increasingly rare. The cosmic engines that once shaped reality have exhausted themselves. The universe reaches a condition where almost every process capable of occurring has already occurred. Yet even here, mysteries remain. Physicists do not know with certainty what happens on the largest timescales imaginable. Some theories suggest the universe may continue expanding forever. Others propose that space itself could eventually experience dramatic transformations. Quantum fluctuations may produce rare events across unimaginable stretches of time. Some speculative ideas even suggest entirely new universes could emerge from conditions we do not yet fully understand. The truth is that the far future remains one of the greatest unanswered questions in science. The further we travel into time, the more uncertain our predictions become. Our understanding of stars, galaxies, and black holes rests on observations and well-tested physical laws. But when discussing intervals of time that exceed 10 to the power of 100 years, we begin entering territory where knowledge becomes increasingly limited. The universe may contain surprises that no human theory has yet imagined. And perhaps that is fitting. Throughout history, every generation believed it understood the boundaries of the cosmos, only to discover something larger beyond them. New planets. New galaxies. New laws of nature. Every answer revealed deeper questions waiting beyond the horizon. The future may prove no different. What makes this story remarkable is not merely the fate of stars or galaxies. It is the scale of the universe itself. Human lives unfold across decades. Civilizations rise and fall across centuries. Recorded history occupies only a few thousand years. Yet the cosmos measures its future in trillions, quadrillions, and numbers so vast that ordinary intuition breaks down completely. We exist near the beginning of that story. The stars still shine. Galaxies still glow. The universe remains filled with light and structure. Every sunset. Every moonlit night. Every star visible in the sky belongs to an era that future ages will remember as the age of abundance. We happen to live during one of the most active and beautiful chapters in cosmic history. One day, that chapter will end. The stars will fade. The galaxies will grow dark. Black holes will disappear. Matter itself may dissolve into the emptiness. The universe will continue its journey into a future almost impossible to imagine. Yet the fact that these endings lie ahead does not diminish the wonder of what exists today. If anything, it makes the present universe even more extraordinary. Because for a brief moment in cosmic history, the universe became aware of itself. Atoms forged inside ancient stars assembled into living beings capable of asking questions. Tiny creatures on a small planet learned to study the cosmos and imagine its future. The universe produced observers who could look into the darkness and wonder how the story ends. And perhaps that is one of the most remarkable events of all. Long after the stars have vanished and the galaxies have faded from sight, the story of the cosmos will continue. Whether the future brings endless expansion, ultimate stillness, or something entirely unexpected, the universe remains larger than any single answer. Larger than any civilization. Larger than any age of stars. The lights may eventually go out. But the mystery remains.